Welcome to lecture number 15 for EE206 Circuits 1, Instrumentation Amplifiers. Now, instrumentation amplifiers are something we looked at in our last lecture. It's an op-amp circuit where the gain is a ratio, R1 over R2, times the difference between two inputs, A minus B. This is an extremely versatile circuit. You can build inverting amplifiers, non-inverting amplifiers, differential amplifiers. Is used extensively with sensors, meaning instrumentation. Here I'd like to give a couple examples of things you can do with an instrumentation amplifier. The first one is voltage amplification. Now with microprocessors, typically the output of something like a digital to analog converter is a 0 to 5 volt signal. If I want to amplify it and shift it so that the output becomes plus minus 10 volts, then this can take the microprocessor output, a 0 to 5 volt analog signal, and change it to a plus minus 10 volt signal, which can then drive a speaker, drive a motor, drive other things, anything between minus 10 and plus 10 volts. To do that, I need a gain and an offset. The input has a range of 0 to 5 volts. The output is minus 10 to plus 10, so the gain is output over input. The output changes by 20 volts, input changes by 5, the ratio is 4 to 1. So Y is 4 times X. In addition, when X is 0, Y is at minus 10, so it's 4X minus 10. I can rewrite that as 4 times the quantity, X minus 2.5, which is the instrumentation amplifier. The gain is 4, a 4 to 1 ratio. X goes on the plus input as a positive gain, and the minus input is 2.5 volts. So this is kind of a multiplier and a level shifter. Convert the 0 to 5 volt signal into a plus minus 10 volt signal. That's one application of an instrumentation amplifier. Second application is an ohm meter. Suppose I want to convert a resistance, say 2000 to 2200 ohms, to minus 10 to plus 10 volts. Instrumentation amplifier can do that too. The trick is first convert resistance to voltage, and one way to do that is a voltage divider. This resistor is kind of arbitrary. It tends to work best if I pick it somewhere near the middle of the resistance range. So I'm going to pick it to be 2100 ohms. Then using voltage division, I can find that Vx goes between 4.8 volts and 5.1 volts. And ideally, when X is 4.8 volts, I want the output to be minus 10. When X is 5.1, I want the output to be plus 10. So I'll then connect this to my instrumentation amplifier. And notice that as the input, as X goes up, the output goes up, which means I connect to the plus input of the instrumentation amplifier. And that looks like this. So the voltage divider connects to the plus input. The gain I need, gain is output over input. The output changes by 20 volts. As the input changes by 0.2 volts, gives you 83 to 1 ratio. So pick this to be 83.95 to 1. The output should be 0 volts when A and B are equal. When I'm at at mid-band, 4.997 volts, the output should be 0. So make the offset 4.997 volts. What that does then, as the resistor goes from 2000 to 2200 ohms, output goes from minus 10 to plus 10 volts. If I check that in Circuit Lab, what I can do is build a circuit and then sweep. I'm going to sweep R2 to go from 2000 ohms to 2200 ohms. And then look at the output. When I do that, it goes from minus 10 to plus 10. Almost. The reason it's slightly off is because when I did the voltage divider, I ignored R5 and R6. If you include those, this is actually 850K to ground in parallel with R2. What that does is that drops the resistance, the net resistance seen at R2, which drops the voltage to V1, which drops the voltage to V5. So likewise, the analysis we did is a little bit off. I can adjust that by adjusting V6 to bring these back to minus 10 to plus 10 volts. But that's what the output looks like. And it's also not exactly linear. There's a slight bend in this. That's because voltage division is nonlinear. I'll get a little bend when I convert resistance to voltage using voltage divider. Third case. Let's do a thermistor, RTD sensor. An RTD sensor is a temperature sensor where the sensor is made out of metal. In this case, it's copper. All metals are sensitive to temperature. As temperature goes up, the resistance goes up. Not a lot, but a little bit. For copper, the resistance goes up as 0.43% per degree C. So this would be the equation of resistance versus temperature for a piece of copper wire, in this case a copper temperature sensor, an RTD. If I want to convert this to voltage, I want to go from 0 volts to 10 volts as I go from 0 to 100 degrees C. What I need to do is first convert resistance to voltage. That's the voltage divider. Here, kind of arbitrarily, I chose 1,000 ohms. At 0 degrees C, R is 1,000, so VA will be 5 volts. At 100 degrees C, R becomes 1430 ohms. Again, not a huge change, but there is a change there, meaning the output VA goes to 5.885 volts. Note that as R goes up, VA goes up. As VA goes up, the output goes up. Here's a positive correlation, so I connect to the plus input on the instrumentation amplifier. The output should be 0 when I'm at 0 degrees Celsius, or A is 5 volts, so make the offset B 5 volts. The gain that I need is output over input. Output changes by 10 volts as the input changes by 0.115 volts. So I need a gain of 11.3. Pick this to be 11.3 to 1 ratio. So that should convert temperature to voltage. If I check in MATLAB, as temperature goes between 0 and 100 degrees Celsius, here's the resistance. By voltage division, this is the voltage. The output is then gain times VA minus VB, and plot. And you get this curve. And going from 0 to 10 volts. Throw that in Circuit Lab, and sweep R2 between 1,000 and 1430 ohms. And you get, goes from 0 volts to 10 volts. Again, here it's slightly off. The reason it's slightly off is because I've ignored R5 and R6 in my analysis. Circuit Lab doesn't ignore those two. It takes that into account. These two are basically in parallel with R2. That reduces R2 slightly, which reduces V1 slightly, which reduces the output slightly. And that's why you see the output is slightly different. And that's fairly typical. Your analysis is slightly different than the actual output because I made some simplifying assumptions in my analysis. If you simulate it, you'll get a better approximation. Build it in lab, I'll get it even better. Fourth case, let's look at a thermistor. A thermistor is a piece of silicon that measures temperature. In this case, the temperature resistance relationship is this, highly nonlinear. Nice thing about thermistors is the resistance changes by a lot. So as we go from 0 to 40 degrees Celsius, that thermistor is going to go from 3,300 ohms to 533 ohms. Design a circuit that goes from 0 to 10 volts as temperature goes between 0 and 40 C. So again, the trick is first convert resistance to voltage. I chose a 1K resistor, somewhat arbitrarily. What that does as I go from 0 degrees C, meaning 3320 ohms, V will be 7.68 volts. At 40 degrees C, VB is 3.47 volts. I want to take a circuit that converts 7.68 volts to 0 volts, 3.47 volts to 10 volts. And notice as the input voltage goes down, the output goes up. So in this case, I'll connect to the minus input. Going down here. The offset, I want the output to be 0 when these two match. I want the output to be 0 at 7.68 volts at 0 degrees C. There's the offset. The gain I need is then change in output over change in input. Output changes by 10 volts as the input changes by 4.2 volts. Gives a gain of minus 2.3. So pick this to be 2.3 to 1. If I then check in MATLAB, given the temperature, find resistance. Given resistance, find voltage. Given voltage, find the output voltage and plot. Goes from 0 to 10 volts as temperature goes from 0 to 40 C. That checks. Go into Circuit Lab. And this is kind of one way to check it in lab. I want to vary temperature. If you have a controlled temperature chamber, I can do that. Otherwise, what I can do is use a decade resistor box. The circuit doesn't know or care how you generate R2. I can check the left endpoint. When R2 is 3320 ohms, that corresponds to 0 degrees Celsius, find the output. At midband, at 1250 ohms, find the output. And at the top end, when its output should be 10 volts, at 533 ohms, find the output. So given this circuit, I can run 3 DC simulations at 0 degrees C, the corresponding resistance, I should be 0 volts out. It's actually 0.042 volts. At the midband, I should be 5 volts out. At the high end, I should be at 10 volts. And so there I've actually done what I wanted. I've gone from 0 to 10 volts as temperature goes between 0C to 40C. That's kind of things you can do with instrumentation amplifiers. Very useful, especially in converting resistances and other types of sensors to an output voltage. The real power is the instrumentation amplifier doesn't care what the sensor is. As long as it's resistive in nature, it'll convert a resistance to a voltage. Change the sensor from a temperature sensor to a different sensor. I can now measure color, current, level, flow, forces, gases, humidity, magnetic field, motion, pressure, proximity, shock, strain, temperature, touch, distance. DigiKey sells, I think last time I counted, over 19,000 different sensors. Almost all are resistive in nature. So by just buying one of these sensors and putting that into your circuit for R2, I can now measure temperature, pressure, flow, light, flow, force, dust, magnetic field, pretty much anything you want. This is an extremely versatile circuit and very commonly used. That's lecture number 15 for ECE 206, Circuits 1, Instrumentation Amplifiers.